Okay, so homologous series recap. Homologous series of alkanes. CN, H2N plus 2. Yeah? Nothing fancy about that. We could say that it's saturated. Right? We could say that it's all single carbon-to-carbon bonds. Name of the functional group. If I've got anything that's just a hydrocarbon, we refer to it as alkyl. So it's going to be the same for alkyl. Yes. The one I handed out is not the same as this. This is you've already been given this. Here's summary sheet. It's got that at the top. Okay. Example. Butane. What type of intermolecular forces in alkanes is dispersion only. Polarity? Non-polar. Soluble in water? Nil. Insoluble. Typical reactions which we haven't gone through, but yes, combustion. Not of alkanes, no. Alkenes, yes. Combustion. And we'll go into this next topic, halogen substitution. So, yeah, that's right, substitution reactions. Nil, yeah, non-soluble. Insoluble. I did not bring any with me today. It is, I believe it's on Canvas under activity if you want to get it and then just annotate. It is a Word document. Yeah, so if you want to annotate on Canvas, you can download it. Alkenes, CnH2n, unsaturated, right? One carbon-to-carbon double bond. Right. Name of the functional group, ene. Yeah, the ene functional group. That's in terms of naming, yeah? Example, but1-ene. No cis or transform for but1-ene. No cis or transform because we've got two of the same substituents coming off one of the carbons. Dispersion only, non-polar, insoluble. Still combustion. And different to alkanes. Alkanes goes under substitution reactions. Alkenes undergo addition reactions. Yeah? Alkanes can also go under what's called subtraction examples, but that's not something we explore in BCE. Essentially, we can take an alkane, subtract H2 from it, and form alkenes if we want to. Alkynes, CnH2n minus 2, unsaturated, right, it's got a carbon-to-carbon triple bond. I guess if we want just some additional notes to consider is that around a double bond has a planar structure, around single bonds has a tetrahedral geometry, and around triple bonds is a linear geometry. There is, but not under standard conditions. Ine is the functional group, so if we will look at but1-ine as the example, C triple bond C carbon-carbon single, no hydrogens around that carbon. So be mindful of common mistakes is that when drawing structures quickly is that around this carbon here or this carbon here, students will add additional hydrogens. Yeah. That just says planar. Yeah. Sorry, it's not very clear. But1-ine, right? Dispersion only, non-polar, insoluble. Right? it's a hydrocarbon, does undergo combustion reactions. Also available, we can do addition reactions with alkynes, but we don't explore. Right, we don't explore reactions of alkynes in Year 12. But yeah, any hydrocarbon, right? Any hydrocarbon can undergo combustion reactions. It's not that it can't, right? Yes, combustion as well. But more likely, right, it's going to be an incomplete combustion reaction because that triple bond requires enormous amounts of energy to break, very strong bond, so you're not really going to use an alkyne as a fuel, for example, because it requires too much energy to get the energy out of that triple bond. Now, a question about physical properties of alkanes, alkenes, and alkynes for you to consider. Of the three, which has the highest? So if we look at butane versus butane versus but1ene, which has the highest boiling point? One says butane, someone says butane. All right, so look them up. You're going to look up butane, you're going to look up butane, and someone else look up butene. Kinsey, can you do that? Look up butane. Right, we've got to think about dispersion forces. Yeah. Of those three examples, either, it doesn't matter. Boiling point. Right, so butane is -1 degree, yeah? So if we consider boiling point. So if we think the boiling point of this is -1 degree, and but1ene, yeah, they're not very stable. We're talking boiling point, physical properties. Instability of bonds relates to chemical properties, yeah? So boiling point of but1ene is what? Okay, butane, 8 degrees. Cool, what's but1ene? Cool, boiling point, -6.3. -6 degrees. So we can see that of those three, butane has the highest boiling point. Now, if we compared ethane versus ethane versus ethene, ethane actually has the highest of the three, but as we get the longer hydrocarbon, alkynes have the highest of. In this example, alkynes have the highest. Why? What is it about alkynes? Yes, to break the bond, but remember, boiling point relates to intermolecular forces, not intra. No? It's not polar. No, all of those are non-polar. No, nothing to do with the bonding between the carbon atoms. Intermolecular forces. Linear. Why? What's that got to do? Aha. Linear structure means we can more closely pack the molecules. If I can closely pack, I'm getting those closer together, greater amounts of dispersion forces. Yeah? Why is alkenes lower boiling point than alkanes? Yeah? Yeah? So alkynes more closely packed, but why do alkenes not more closely packed? Right, no rotation around the double bond, yeah? Geometric isomers. Because there are no rotation around the double bond, they do not closely pack, yeah? They are hindered in the way in which they can pack. So alkenes, lowest boiling point, followed by alkanes, followed by alkynes, generally speaking. Some exceptions to the rule, so not all alkanes and alkynes will follow that pattern, but generally speaking. Cool. The other thing to consider is the position of the double or triple bond. What effect does that have on the boiling point? So can I have a volunteer to look up the boiling point of butene.
It says 0.8 to 3.7.
So butene is higher.
Yeah.
Okay. Yep. All right. And what about but2-ine? Higher or lower?
27 degrees.
27 degrees. Right, so even higher. Yeah? That relates to closely packing of the molecules. Okay, moving on. Haloalkanes. Rather than CN whatever, right, I'm just going to go RX, where X is equal to fluorine, chlorine, bromine, or iodine. Really, it's a CnH2n plus 2, reduce that by 1, and replace with a halogen. Yeah? CnH2n plus 1, X. In terms of naming, we'll have the prefix, right? If it's fluorine, it will be fluoro, chloro, bromo, or iodo. Yeah? Fluoro, chloro, bromo, iodo as a prefix in terms of naming. You could have all of them. Yeah? Yeah, you could. You could have all of them. Yeah. All right. And simple example. Put a chlorine there. So my example is 1-chlorobutane. Now, intermolecular forces. Yeah, intermolecular forces between chlorobutane molecules. What would they be? Yep. What's the most significant form of intermolecular force? Jacob? Jacob, you can answer this. What is the most significant intermolecular force between haloalkanes? Most significant. Dipole. It's correct. Now, it's great that you're all mentioning dispersion because it's dipole and dispersion. In fact, it will be and dispersion for every homologous series. Yeah? But yes, it has dipole. Why does it have dipole? Because it's polar. It has a polarized bond, therefore it is polar. Right? Chlorine, slightly more electronegative than chlorine and hydrogen. It has a greater share of the electrons. So we've got a slightly polar end. If it's polar, what does that mean? Right. Now, in the case of haloalkanes, it is slightly soluble.
We found the compound fluorochlorobromoiodobutane.
Cool. Yeah? And that is a chiral molecule.
Yeah.
Yeah? Okay, this also undergoes substitution reactions. In fact, I'll get into it, but more specifically, it undergoes what's called nucleophilic. Yes, all of them will undergo combustion, right? All hydrocarbons will undergo combustion. I'm just giving the additional, other. It says nucleophilic. Yeah? I'll get into that later. Don't really need to know what nucleophiles are, but just substitution. Yeah, so what happens with haloalkanes is the chlorine is a great leaving group. It puffs off and something else will go into its place. Now, looking into boiling points. What's the boiling point of 1-chlorobutane? 1-chlorobutane, what is that? Look it up, quick. Chlorobutane. Right, so 2-chlorobutane is 68 degrees. right? So if we change the position of